Hi everyone, my name is Yasaman Nemati. I'm a PhD student in geophysics at Laval and I work under the supervision of Professor Dupuis, Giroux, and Smith. And today I'm here to talk about some part of the results from my PhD studies with the title of Response of Normal Resistivity Tool in Orogenic Gold Deposit. My study area is Rouen property, which is located in south of Rouen, Noranda town in west of Quebec, and it is located in south of Abitibi sub-province. It's an orogenic gold deposit that spans 12 kilometers along the Cadillac-Larder Lake break. Here we see the different lithology group that exists in my study area. Our focus of the study is Pische group, which is made from talc chloride carbonate schist. Pische group is known to be the physical expression of Cadillac-Larder Lake break in my study area, and it is the main target for the gold exploration. Gold in Piche happens as free gold in association with quartz carbonate veins, and it also happens at inclusions or filling of fractures uh, in association with sulfides. We gathered the petrophysical data from 7 boreholes along this study area. So, based on the occurrences of the gold, we divided our study area into two main zones. The first zone is sulfidation dominated zone, which is characterized by the sulfidation, and the second zone is quartz carbonate vein dominated zones, which are the sections that have a high number of quartz carbonate veins. For this presentation, I will only focus on the quartz carbonate vein dominated zones. So we realize that when we plot the normal resistivity data in 8-inch versus the 64-inch, we see two general behavior. The first behavior is that when the data fall alongside of the one-to-one line, and when they have a vertical behavior. So what does it mean? It means that the first group we are having like a homogeneous rock. It means that whatever the 8-inch electrode sees, the 64-inch electrode also sees. And the second group is that the N8 increases up to a certain point, but that's N64 that is still increasing. So that's why we are having these vertical trends. The reason for that can be explained by that the fact that there's something resistive in 64-inch sections that it does not exist, or it does not exist as much as the 8-inch section. So we believe that those resistive features are those quartz carbonate veins that we discussed. To check the idea, we picked one of our boreholes and we counted the number of the veins along the Piche. So, in order to include the effect of the vein thickness, we also multiplied the number of veins in each section into their average vein thickness. So we see that in general, we see a decrease in our data from 103 almost to 130. So if we plot the N64 data over the same sections, we see that those sections that we saw an increase in our data matches the section that has the highest N64. So it means that probably the veins are the reason for increase in N64. We also plotted the ICM log over the same section of the data. We saw that the section of the data that are having the highest number of veins and the highest N64 matches the ICM data that are having the warmest color. In order to explain for you, ICM means comes from the image complexity map. It is an automative generated log from the OTV images that basically based on the complexity of the image that the OTV sees gives the value between 0 to 1 to the data. And as the image gets more and more complex, it uses the warmer color and gives a higher value to the data. Just to give you an example, on the left, we see that we are having a section with warm colors. The image in the OTV seems more complex. And if we look at the core images, we see that there are many veins here. However, on right, we see that we are having like cool colors. The image of the OTV and the core images show that basically the rock is way more homogeneous in comparison to the image on the left. We also plotted the P wave versus the S wave. And we saw that the section of the data that have the quartz carbonate vein dominance, they generally have higher values for P wave and S wave in comparison to the sections without the vein. So the reason for that can be explained by the fact that the acoustic wave travel faster in quartz in comparison to the schist. So now that we realize that basically the quartz carbonate veins can affect our logs, we decided to see if we can model the effect of each vein parameter on the resistivity tool. So we created a 3D finite element model of our tool, vein, and borehole, and we assessed the effect of the vein thickness, vein radius, vein angle with the borehole, and also vein resistivity, plus the effect of the borehole fluid resistivity. For this presentation, I will only talk about the effect of vein thickness, vein resistivity, and the borehole fluid resistivity, and I will only show the results for the 64-inch electrode and the 8-inch electrode. Before going to the results, I would like to show you some slides on how my next plots are going to work. So imagine I have a 13-meter thick vein. So I know that in reality, we might not have this case, but you can consider this as a package of vein, as a stock work of vein. So as the tool passes along this vein, it will give us a curve like this. So on x-axis, we have the apparent resistivity, and y-axis, we have the electrode distance to the center of the vein. So this gray shaded areas is showing the thickness of the vein, and we have a curve like this. If I change the thickness of the vein, I will have another curve, and then if I still decrease the thickness of the vein, the next curve would be like this, and the shaded areas show the different thicknesses. So now let's go to the results. So here I'm showing you the result for a 1 gigaohm resistive vein, and I'm changing the thickness. On right, I have the result for 64-inch electrode, and on the left, I have the result for 8-inch electrode. If we compare the result, we see that as the vein becomes more and more thicker, the N64-inch electrode will read better values, or values closer to the actual resistivity of the vein in comparison to the 8-inch electrode. If we compare the vein boundaries, we see that the N8 electrode reaches its maximum value sooner than the N64 electrode. So it means that the N64 electrode is more affected by the vein boundaries in comparison to the 8-inch electrode. And then if we look at the data for vein thicknesses smaller than the electrode spacing, we see that both electrodes will treat the resistive vein as a conductive feature. The reason for that can be explained from the results in ParaView. So here we are having a 20 centimeter thick vein, or 4-inch vein. So we see that how the path of electrical current prefer to go around the vein instead of going through the vein, because the vein is really resistive. And this will cause to have a equipotential surface distribution like this. So we see that the potential drop before the vein is way higher in comparison to the after the vein. So it means that the 64-inch electrode here will have less potential drop, so it will read a lower resistivity comparison to the thick vein. And now here we are seeing the results for the effect of the vein resistivity for 6.5 meter vein. So we see that for very resistive vein, that's the 64-inch electrode that will read higher values, and values closer to the actual resistivity of the vein in comparison to the 8-inch electrode. However, for the uh, conductive veins, we see that that's N8 that will have better separation for the different curves in comparison to the 64-inch electrode. And in general, we see that basically there's a limit for the tool. So in our model setup, the limits that we have are these two curves that I drew here. So it's 10 to power of 6 and 10 to power of minus 3. So it means that basically, even in theory, the tool cannot go above these values for the measurement. So if we have a vein more resistive than this value, it's gonna fall exactly on the same curve. And for the effect of the borehole resistivity, here I'm showing the results for the 6.5 meter thick vein with a resistivity of 1 gigaohm. And we see that as the borehole fluid becomes more and more resistive, it will give us better results in comparison to the conductive veins. And now let's go back to the original N8 and 64 plots. I would like to see if I can understand how this plot works. So to better understand it, I plotted the N8 and N64 curves for the same vein here. So the vein thickness is 6.5 meter and the resistivity is 1 giga. So let's try to understand the curve. So as the tube comes up and gets closer to the vein, N64 electrode, because it has a bigger spacing, will sense the vein sooner in comparison to the 8-inch electrode. So that's why we go above the line for the one-to-one line for the first part of the data. As we reach to the vein boundaries, we see that that's an 8 that will reach to its maximum value sooner than the 64-inch electrode. So that's why we go below the line. And as we reach to the center of the vein, that's N64 that will read higher values in comparison to the N8. So that's why we go above the line. And as we leave the vein, we see that we go back to our original place. There's an important point here. As you can see, the green points and the blue points are not falling on top of each other, and it's because of the relative position of the injection electrode in comparison to the vein, and that's why they do not fall on top of each other. So now let's try to see the effect of each vein parameter on N8 and 64 plot that we have. We start with the effect of the vein resistivity. So if we increase the vein resistivity, we see that the plot starts shifting towards right. And the important point here is that up to a certain vein to rock resistivity ratio, the N64 might never go higher than N8. For the effect of vein thickness, we see that as we are increasing the vein thickness, the only change that we have is that the portion of the data that goes above the one-to-one line increases. And then for the borehole fluid resistivity, we see that how as the borehole fluid becomes more and more resistive, it completely shifts our data towards right. And if we have a very conductive fluid, it moves our data completely above the one-to-one line. So it's really important to measure the effect of the borehole, measure the borehole fluid resistivity when we are using the normal resistivity tool. So going back to our original data, I decided to pick one of my boreholes and if I can to see if I can model this data with my model that I created. So here I'm showing you the OTV, ICM, and the two resistivities. We see that the OTV shows different veins here, and how the ICM shows that it's a very complex section. So we have the thickness of this section, which is almost 14 meter. From the green section, we have the resistivity of the rock. And because the data fall above the one-to-one line, so we know that the fluid is very conductive. So using three values, I try to generate the data that I have. So it's a work in progress. I just wanted to show you that what we are working on right now, but it still needs improvement. But it was great to see that using only three factors, we could get close to our original data. And I'm sure if we consider the effect of other parameters like the vein radius, for example, we can get even closer to the actual data. And now I would like to go back to the original data again. And this time I'm coloring the data based on the gold endowment. So we see that this portion of the data that have the highest gold endowment matches the peaks in our N8 and 64 plot. So it means that basically we can find the probable locations for the highest gold endowment using our N8 and 64 plot. So in conclusion, we saw that the quartz carbonate veins have an important role in detection of gold deposit. We saw that the resistivity logging can help us map the vein geometry and gold endowment. We saw that the 64-inch electrode is best suited for the thick and resistive vein. However, the 8-inch and smaller electrode spacing are better suited for thin and conductive veins. We saw that the how borehole fluid resistivity can really shift our data, so it's important to measure them. And we saw that our result can help us enhance the gold exploration for the complex geologies. Thank you so much for your attention.